Hi everyone. So let me discuss permutation of a group. So to define this, we need the definition of one and onto function. So that is a bijection function definition. Function means one is every element of A has a unique element in B, and onto function definition is every element of B has at least one element in A. So that type of set we have to consider here. Okay, a function which is one as well as onto. So okay, to define a permutation of a finite set S is a bijection, that is one as well as onto mapping from set S to itself. A permutation of a finite set is a bijection from S to itself. From S to itself, and that should be one and onto. In other words, we can define this as, if S is a non-empty set, then a one and onto mapping from S to S is called as a permutation on S. If S is a non-empty set, then a one and onto mapping from S to itself is called as a permutation on S. So notation for this is, let S be a finite set of elements of n elements. So S is equal to A1, A2, A3, AN. Then permutation of F is equal to A1, F of A1, A2, F of A2, A3, F of A3, AN, F of AN, F of AN. A1 image is F of A1, A2, F of A2, A3, F of A3, and AN, F of AN. So here I consider set S, that is S is equal to 1, 2, 3, 4, F from S to itself. So here F of 1 image, 1 goes to 2 and 2 goes to 3, 3 goes to 4 and 4 goes to 1. So here then F is equal to 1 is F1, 2 is F2, 3 is F3, 4 is F4. So your F1 value is what? 2. F1 value is what? 2. F2 value is what? 3. F3 value is what? 4. And F4 value is what? 1. So here every element have a unique element. Okay, and this also have a unique element. Okay, unique element. So this satisfies the definition of your permutation. Therefore this is an example for a permutation. So degree of a permutation, the number of elements in a finite set S is called the degree of the permutation. The number of elements in a finite set S is the degree of the permutation. So next, the definition, so that is symmetric. Okay, so if A is a set containing n elements, then the group of all permutations of A is called symmetric group of A on n elements, and it is denoted by Sn. If A contains n elements, then Sn contains n factorial elements. Okay, if a set contains n elements, then Sn contains n factorial elements. For this example, S3 is equal to 1, 2, 3. Consider the permutation F1 as 1 goes to 2, 2 goes to 3, and 3 goes to 1. We can write this as 1, 2, 3 because 1 goes to 2 and 2 goes to 3 and 3 goes to 1 in a cyclic form 1, 2, 3. Okay, so F2, 1 goes to 3 and 2 goes to 1 and 3 goes to 2. So we can denote this by 1, 3, 2. 1, 3, 2. So F3 as 1 goes to 3 and 2 goes to 2. 2 goes to 2. So if this element goes to same, then we won't consider that 1 goes to 3 and 3 goes to 1. So 1, 3. F4, 1 goes to 2, 2 goes to 1 and 3 goes to 3. We don't consider 3 goes to 3, so we only consider 1 goes to 2 and 2 goes to 1. We can write it as 1, 2. This as 1 goes to 1, we neglect it, 2 goes to 3 and 3 goes to 2. So 2, 3. Next, this is the identity permutation. 1 goes to 1, 2 goes to 2 and 3 goes to 3. So that is only 1, value is 1, identity permutation. Okay, so here next definition is properties of permutation, in that equality of two permutations. So when two permutation becomes equal, okay, so let F and G be two permutations then they are called equality of two permutation if and only if f of a equals z of a for all a belongs to S. So that is image of every element of S under both f and g are equal. Both f and g are equal. So here I take an example, that is f is equal to 1 goes to 2 and 2 goes to 1. So here z we take it as 2 goes to 1 and 1 goes to 2. Okay. So those two are equal because 1 goes to 2, 1 goes to 2, 2 goes to 1, 2 goes to 1. Okay. So then we can write f is equal to z because 1 goes to 2 and 2 goes to 1. Here also 2 goes to 1 and 1 goes to 2 equal. So next example is, so here I take f is equal to 1 goes to 3. Okay. So here also 1 goes to 3, 2 goes to 4, 2 goes to 4, 3 goes to 2, 3 goes to 2, 4 goes to 1, 4 goes to 1. So here in f1 is equal to 3 and here 3 is z1. Okay, z1. So f2 is equal to 4, here 4 is z2. f3 is equal to 2 and here z is so 2, z is, and 2 goes to f3 is equal to, f1 goes to, your f1 is 3 and here 3 is z1. So here f3 is 2 and here 2 is z3. So next f4 is 1 and your 1 is g4. So therefore f of a is equal to z of a for all a belongs to S, that is 1, 2, 3, 4. Okay. So in the next is this is equality of permutations. So next we consider, so that is inverse permutation. So that is I have taken here. So this is the definition, that is here we take, let f and g be any two permutations. If f into g becomes identity permutation, then f and g are called inverse to each other. So here an example is that so f is equal to 1, 2, 3, 2 goes to 4, 3 goes to 3, 4 goes to 1. So here we have to find f inverse. Okay. So here I am taking g be the inverse permutation of f. So we don't know g is equal to 1 goes to which value, I don't know that. So I am taking that as x, 2 goes to y, 3 goes to z and 4 goes to w, because I don't know 1 goes to which value, 2 goes to which value and 3 goes to which value and 4 goes to which value. But we know that f into g is equal to I. So here f into g, f is this and g is this. Okay, f into g is equal to what? Identity permutation, that is 1 goes to 1, 2 goes to 2, 3 goes to 3 and 4 goes to 4. Okay. So here 1 goes to 2 and 2 goes to y. So 1 goes to y, product of two permutations. Okay. So product of two permutations. Okay. So this is the product. So 1 goes to 2 and 2 goes to y. 2 goes to 4, 4 goes to w. 3 goes to 3 and 3 goes to z. 4 goes to 1 and 4 goes to 1 and 1 goes to x. So this is the product of two permutation. Like that we find the product of two permutation. 1 goes to 2, 2 goes to y. So 1 goes to y. 2 goes to 4, 4 goes to w. 3 goes to 3, 3 goes to z. 4 goes to 1, 1 goes to x. So this is equal to identity permutation, that is 1, 1, 2, 2, 3, 3, 4, 4. Okay. So here value of y is 1. W is 2, Z is 3 and X is 4. Therefore G inverse is equal to, so not G inverse, so that is F inverse is, so this is F inverse is, so here we replace the value of 1, so X is 4. Okay, this is F inverse. So 2 goes to y and y is 1, z goes through means your 3 goes to z, and here z value is 3, and 4 goes to w, and w value is 2. So this is the inverse of f. So if we multiply these two, then we get identity permutation. So that is so here 1 goes to 2, and here 2 goes to 1, so 1 goes to 1. So next 2 goes to 4, and 4 goes to 2, 2 goes to 2. Okay, so next 3 goes to 3, here also 3 goes to 3. Next 4 goes to 1, and 1 goes to 4. So here we get, if we multiply these two, then we get I. So that is identity permutation. So therefore the inverse permutation of f is this. So next, identity permutation. So let S be a finite set. Let S be a finite set of n elements. Then permutation of f is called the identity permutation if f of a is equal to a for all a belongs to S. Example for this is S is equal to a1, a2, an. So here a1 is f of a1, a2 is f of a2, an is f of an. So here example for this is, so 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. Okay, 4 goes to 4. So same element. Let S be a finite set of n elements, then the permutation of f is called identity permutation if f of a is equal to a. So a1, a2, an. So 1, 1, 2, 2, 3, 3, 4, 4. So product of two permutation or composition of two permutation. So let f and g be two permutation of a, then the product of two permutation is also a composition of permutation. So f into g of x is equal to f into fog of x, or f into g of x. So here we take an example, that is, let f is equal to 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1, and g has 1 to 3, 2 to 4, 3 to 4, 3 to 2, 4 to 1. Okay, find fg and gf. So fg of x can be written as f dot fog of x, or f into g of x. Okay, so fog of 1, so f into g of 1 is, so this is 1 goes to this can be written as f of g1. So your g1 is what? G1, 1 goes to 3. Okay, 1 goes to 3. So here I am writing f of 3, and f of 3 is what? 4. So next, fog of 2. So f into z2, this can be written as f into g2, and g2 is what? G2 goes to 4. F4 is what? 1. So next, fog of 3 goes to 2. So f of 2, here 2 goes to 3, the value of f2 is what? 3. Fog of 4, f of g4 is what? 4 goes to 1. F of 1 goes to what? 2. Like that we have to find the value of this. Otherwise simple calculation for this is, so 1 goes to, simply you can write f into g is as, so here product of these two can be written as, first 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. So product of into 1, 3, 2, 4, 3, 2, and 4, 1. So here product of this two, 1 goes to 2, and 2 goes to what? 4. So therefore 1 goes 1 to 4, 2 to 3, 3 to 2. So therefore 2 to 1 goes to 2, and 2 goes to 4, 2 goes to 3, 3 goes to 2. So here 2 to, next 3 goes to 4, and 4 goes to 1. 4 goes to 1 and 1 goes to 3. 4 goes to 1 and 1 goes to 3. So this is the product of f into z. F into z. F into z is what? 1 goes to 4, 2 goes to 2 and 3 goes to 1 and 4 goes to 3. So next, g into f, that you calculate it, whether these two are equal or not, you check it. Okay, so here I have found f into g like this. So in the similar manner you try it, z into f. Okay, so next is cyclic permutation. A permutation gamma of set S is a cyclic permutation if there exists a finite subset a1 a2 an of S such that gamma of a1 is equal to a2, gamma of a2 is equal to a3 and gamma of an is equal to a1. So therefore, if gamma of x is equal to x for all x belongs to S and x doesn't belongs to what? a1, a2, an. So then we can write cyclic permutation gamma as gamma is equal to a1, a2, an. a1, a2, an. So a permutation gamma of set S is a cyclic permutation if there exists a finite subset a1, a2, an of S such that gamma of a1 is equal to a2 and gamma of a2 is equal to a3 and gamma of an is equal to a1. So for this example, so here 1 goes to 2, 2 goes to 3, 3 to 4, 4 to 1. So this can be written as 1 to 2, 2 to 3, 3 to 4, 4 to 1. So this can be written as 1, 2, 3, 4. 1, 2, 3, 4. So 1 goes to 3, 2 goes to 2. So we neglect this. If same element is pairing with same element, then we neglect that. 1 goes to 3, 3 goes to 4 and 4 goes to 1. So this is 1, 3, 4. 1, 3, 4. So here another example, let f is equal to 1 to 4, 2 to 1, 3 to 3, 4 to 2 be a permutation, then we can write a cycle as, so your f1 is what? 4, f2 is what? 1, f3 is what? 3, f4 is what? 2. So we can write this as this element pairing with the same element. So we can write this as 1, 4, 2, 1, 4, 2, 1, 4, 2, because 3 doesn't belongs to this gamma, because f3 is equal to 3. So next, so here gamma is 2, 4, 5, 6 belongs to S, be a cycle here. Okay, so gamma of 2 is equal to 4 and gamma of 4 is equal to what? 5. Gamma of 5 is equal to what? 6. Gamma of 6 is equal to what? 2. Okay, so then gamma is equal to, so 2 goes to 4, 4 goes to 5 and 5 goes to 6, 6 goes to 2. But these two have no element, no means here there is no value here, in gamma is not there. So means these are pairing with the same element. Here 1 and 3 is not there because those are pairing with themselves. Okay, so we know that self image element doesn't contain in cycle. So 1, 3 doesn't belongs to 2, 4, 5, 6. Therefore gamma of 1 and gamma of 3, gamma of 1 is equal to 1 and gamma of 3 is equal to 3. Therefore gamma is equal to 1 to 1, 2 to 4, 3 to 3, 4 to 5, 5 to 6, 6 to 2. So like that we pair. Okay, so thank you. If you have any doubts regarding this definition, you can send questions to my WhatsApp number and clarify your doubts.